Algebra 2, set 89, conjunctions, disjunctions, products of chords and secants. So conjunctions, you should recognize from Latin. C-O-N is meaning together. So conjunctions are situations where we're using the word and. Disjunctions kind of means disagree. They both inequalities don't have to be true, so we use the word or. So let's just do a couple of examples. Graph negative x minus 3 is less than or equal to negative 2, and x minus 2 is less than 1. Your domain is integers. So it's a conjunction because it's using and, so both need to be true. So we have negative x minus 3 is less than or equal to negative 2. Add 3 to both sides, and then divide by negative 1. Remember, when you divide by negative 1, you switch the signs. Now let's do the next one. X minus 2 is less than 1. If we add 2 to both sides, we get x is less than 3. So now we'll graph. And we want to graph x is greater than or equal to negative 1. And x is less than 3. Remember, we're dealing with integers here, so we want to graph where they overlap. And where they overlap is from negative 1 to positive 2. So that is your solution. Okay, graph negative 2 is less than, x minus 2 is less than or equal to 4. The domain is the real numbers. So we'll add 2 to all the sides. We end up with 0 is less than x, which is less than or equal to 6. These are pretty easy to graph because we know that what our solution is in between 0 and 6. And so all we have to do when we graph is put our number line, put an open circle at 0, a closed circle at 6, and then color everything in between. Okay, graph negative x is greater than or equal to 3, or negative x is less than negative 1. So in this case, we're not looking for overlap. We're looking for anything to be true in either one. So let's do the first part. Negative x is greater than or equal to 3. If we divide by negative 1, we switch the sign. We get x is less than or equal to negative 3. Or negative x is less than negative 1, divide by negative 1, switch the sign, we get x is greater than 1. So we'll make our number line, and we put a closed circle at negative 3, and we're going to put an open circle, let's shade less than or equal to negative 3, we're dealing with real numbers. And we'll put an open circle at 1, and we're going to go everything bigger than 1. So the solution looks like this. Okay, graph negative x minus 2 is greater than or equal to 0, or x plus 3 is greater than 6. The domain is the integers. So on our first one, add 2 to both sides, divide by negative 1 and switch the sign. The second one, x plus 3 is greater than 6, subtract 3 from both sides. Now we're dealing with an OR situation, and we're dealing with integers. So we want to start with x is less than or equal to negative 2, closed circle, and we're doing integers. And then we have x is greater than 3, so open circle at 3, closed circle on 4, 5, and beyond. Okay, products of chords and secants. So just as a reminder about chords, when you have two chords that are crossing, we have 80 degrees plus 90 degrees divided by 2 will give us that angle of x. So 170 divided by 2 is 85. And then if you have it on the outside, we know that if we take 170 degrees and subtract 90, divide by 2, that will also give us x, which is 40 in this case. So the rest of this lesson is going to be on proofs. So there are 3 different proofs that we're going to do. So the first proof is we're going to prove when chords intersect inside a circle, the products of the chord segments are equal. So an example of what this is talking about is if we take 4 times 3, we will get 2, that is the same as 2 times 6. And then another example, if we do x times 5, that will be the same thing as 3 times 7. So in a minute we'll do a proof to show why that is the case. The second proof is going to be when secants intersect outside of the circle, the products of the external segments and the whole segments are equal. So here's the example of what we're talking about. So if we take 3 and then times it by the total length of that segment, which is 8, it's going to equal 2 times 12. So we can see 24 is equal to 24. Another example, 4 times 4 plus x is equal to 3 times 8. And then the last thing that we're going to do a proof of is if one of the lines is a tangent, one product is the square of the tangent segment. So what this means is if we have 4 times 4 plus x, that's going to be equal to 8 squared. So here's our proof number 1. Products of chords are equal. So if we have 2 chords and they're divided into segments, we have x, y, and a and b. What we're going to do is we're going to connect so that we make triangles out of these intersecting segments. So we can see that the angle, well, here, let me highlight it. We can see that this angle is equal to this angle because they both share the same chord or the same arc, which is RS, so they both have the same measure. We can also say that those 2 angles are equal because they are vertical angles. And if you have 2 angles in a triangle that are equal to 2 other angles in a triangle, we know that the third angle also has to be equal. So these are similar triangles by angle, angle, angle. So since they're similar triangles, we can do, we can set up a ratio. A is to x as y is to b. So if we have a is to x as y is to b, we can cross multiply. AB is equal to yx, and that's what we're trying to prove. A times b is equal to y times x, or x times y. So that's the proof of the first one. Okay, our second proof is the secant segment proof. So we'll take the secant that we have point P that's connecting to point R on the opposite end of the circle and T on the opposite end of the circle. And what we'll do is we'll create 2 diagonals that connect to S and U, and we can see that they share this arc length. So the angle at R is the same arc length as the angle at T. They share the same arc length. So therefore we can say that angle R is the same as angle T. Now we're going to take each of those individual pieces and we're going to make them into triangles. So we're going to eliminate the other piece. So here's our first triangle that we make, triangle RUP, and then we'll have triangle TPS. So since we know the angle R and angle T are similar, we also can see the angle P, since they both connect at SPU on both triangles, that those 2 angles are the same. And since we have 2 angles that are the same, the third one has to be the same. So we know that we have similar triangles by angle, angle, angle again. So if we have similar triangles, we can say that the length RP to the length TP is the same as UP to SP. So RP times SP is equal to TP times UP, which is the secant segment, equation that we were working with before. Okay, last proof, and that is the tangent one. So if we start with the same angle that we did before, we have RPT, that angle. If we take TP and we move it closer to the edge of the circle so that it gets closer and closer to being tangent, and then we actually push it out more so that it actually becomes tangent, you can see what's happening. First of all, angle P is getting bigger and segment TU is getting shorter as we move that TP closer to the edge. And then eventually what's happening is TU actually becomes just a point where T and U are the same point. So when that happens, remember when we're comparing TP to UP, in the second one, we have TP and UP, and we can still multiply them, TP times UP, but when we get to the last one, TP and UP are the same thing, so since TP and UP are equal, we can just say that it's the same thing as TP times TP, or TP squared, which is exactly what we were looking for.